So for my first order of business, I'm going to set up the spot, and the spot is the potentiometer located right here, right over here. And I'm going to do so by, first of all, before I do anything, I want to let this thing warm up and settle down, right? And when I have that done, there is provided on page 31 some standard settings to just sort of bring the scope into something that will provide just a viewable line, so just sort of bring you home to this. We're going to turn the focus all the way down to counterclockwise, right? And we're going to turn the horizontal gain all the way down to 0, and then we're going to turn it all the way down to external input. And we're going to have this dot right here. And what we're going to do then is turn this this knob right here until we get a perfectly round circle. I'll try and zoom in here so we can see if we can do that. And we're going to turn and turn, and it's going to blip back, and then we get this perfectly round spot. That's nice and round right there. And once that's set up over here, then it's done. We can leave it alone. It's over. Right. So now if I go back, I'll put it back on 10. Let me bring the horizontal back to 50, and then I bring the focus back in, get a real nice sharp. That's really sharp. I don't know if the camera does it justice. Got a nice sharp line. Obviously this is very low frequency. Yeah, that looks really good. So that's it. That's the spot is done. Everything at this point is done with the focus knob. Got a clean line. Obviously there's some, you can see it's bouncing a bit because we got nothing tied to the vertical. It's just sitting here floating. If I touch it, you can see some interference there, but that's done. The next procedure should be pretty obvious with this flat line, seeing if the picture tube is correctly placed. And you can see that looking at the screws, that the slant is actually going this way a bit, right? So it's the high side of this screw to low side of that screw. Obviously, common sense would tell you that this should be annotated. It'd be a good time to power down the unit before grabbing a 1200 volt CRT and trying to adjust it. So I'm going to leave this alone for now and make that modification next time I shut it off. Just give a little nudge in that direction and then see where it goes. I'm not going to do that while this is on, just to shut it off to turn it back on again. It's not terribly necessary. In keeping with the actual book, if we were to see the horizontalness of this CRT, to see that the CRT was actually in the right position, we would be connecting this 1 volt peak to peak into the horizontal and setting the sync selector to external, right? With the external setting that we used for setting the beam from the previous step, right? And this would give us this line right here. So the book says that we would then use this line, and with a grease pencil, we would go over this line, and then we'd be able to shut it off and use this line as the guide to set it up. And this is how it is described in this step right here on page 31. The next step talks about taking the 1 volt peak to peak and hooking it up into the vertical. And I believe this has nothing to do with calibration, but more of an exercise of its checking its functionality. Right, so I'll hook that in there, and this is going to be 60 hertz, this waveform, so there's absolutely no way it's going to work at this setting, but there you go. There's that setting, and the vernier will open it up, and it's 60 hertz, so there's definitely some flicker on this. There's very low frequency indeed, right? So I can move it, up and down, right? I could flip it over to see if it syncs, leading or trailing, right? There you go. There's our horizontal gain. Very nice, right? Our horizontal position. I can move it about. Our vertical. Obviously, it's gonna be way too small if I do that, but I could open it up. I could bring it down. That's with the gain all the way down to 10 is the minimum. I imagine I could go to 10 here and then break it out as a multiple. That'd be 100 times. It's pretty much, I guess, the same as 1, right? So, so that's pretty good. So yeah, I guess as an exercise of the functionality of the unit, you know, them allowing you to plug into that. So the purpose of that last exercise is to bring you to the next exercise, believe it or not. And the next exercise wanted a very specific configuration to be done with that 1 volt peak to peak to arrive at this exact picture with this exact number of waveforms, even to the point of showing the detail of these line breaks, you know, caused by the field of the power transformer, you know, that would actually, they wanted this picture, you know, and I got it. So I ended up with that exact picture displayed on the scope. So I got the scope configured exactly how they want it configured, and quite possibly this is a lead-in for the next step. So I shut off the unit and I connected my vertical input around and to this horizontal input wire in the back here. It's labeled as horizontal input, and there's a bit of wire cut away in the original build that allows me to do so. And I've set the selector switch as shown here, and when I turned on the unit, having left all other settings alone except moving this to X10, I was able to get this line set up, getting everything into position and messing with the gains of both the vertical and horizontal until I was able to achieve this line. And this is not what it looked like at first. I've since adjusted it, but I will show you how it looked and how I brought it to this, adjusting for this in the back. And the first one I did is the times 10. So naturally I'm on the times 10 setting here, right? So I get my screwdriver positioned inside this adjustable capacitor, and you can see that if I have it in one direction, it bends that way, and if I go too far in the other direction, it bends that way. So you imagine I just brought it right to the point where it was perfect, you know, and just locked it down at that position. And that's the 10 adjusted. And then all I have to do is, you know, move to 100 and repeat the process again. When you switch from 10 to 100 on the vertical input, you're going to notice that you need a lot more gain, because when you go like that, you end up with almost another horizontal line. So you go like that, and then you're going to have to kick your gain up a lot. I brought mine to 100, and then at that point, you can, you know, come in on the unit right there, and then make your adjustment just like you did on the other one. You know, for my efforts, I already got everything dialed in. And then once both of those are dialed in, that's it. All three adjustments are done. You had the spot and those two, and it's finished. Those are all the calibrations. This is one of the more bittersweet moments of the project, is actually putting the case back on. Can't fiddle with it anymore, you know, but done is done. And now this will be put on the bench. This is ready to go. Also, for the record, you can see 5 megahertz as dialed in on the FieldTech, coming straight into the unit, and we are showing 5 megahertz as displayed. And this is on obviously the highest setting, and the frequency vernier is pretty much maxed out. And you can tell on camera, but it's starting to get, just starting to get a little bit blurry. Definitely acceptable for my needs, but you can see how this is most definitely at the end of what this oscilloscope can do. And yes, I'm sure I could probably get this up to 6, maybe 7 megahertz, but quality would definitely be going down from here. Just case in point, this is 6 megahertz on the oscilloscope right now. So 6 megahertz dialed in, maxed out, frequency vernier, just about 100%. I can stretch it open. The camera does not pick up the ghosting that's going on. You know, I can keep it together by compressing it. Actually, you can see it on camera. And then I can lock it in at the very last, probably the very last one it can do. There's very small amount of bandwidth that it'll lock in on. You know, very tight. Oh, we're talking about just a small amount of area, but yeah, you saw it. 6 megahertz it was able to work at. So there's 6 megahertz. 7 megahertz, you can't see it on the camera, but on the it kind of cleans it up. But on the oscilloscope, it's really broken up. But like I said, I mean, can you see it? Yes. Does it take, you know, several minutes to be able to dial in this waveform? Yes. You know, so for practical purposes, usable? No. But are we looking at 7 megahertz as displayed? You know, yeah, we're looking at 7 megahertz. I've also kicked up the voltage so that it would still be able to be seen, because at 7 megahertz, it's also getting smaller. So that's another thing too. So I've doubled the voltage to keep it looking this big. And here is 8 megahertz. We're looking at 8 megahertz now. I'm afraid if I touch the dial, it'll be gone forever. But let's see what happens. Oh, there it is. It's gone. Yep, never coming back. That was 8 megahertz. Before checking the frequency response of the scope, I got to check the frequency of the field tech, because it's kind of garbage. But it's not too bad in this scenario. Going from 1.09 volts for 1 volt at 100 hertz to the same thing at 1 kilohertz to 1.1 at 1 meg, pretty much staying the same up to around 4 meg, dropping to 1.09 and 1.08 at 5 meg. According to the specification of the Nyquist frequency, there should be a +1 or -1 decibel variation for frequency response between 8 cycles per second and 2.5 megacycles. So taking that value, what I end up with is 1.23 volts or 0.98 volts based on these values. So I'm going to compute that at 1 kilohertz, which is what the reference is being used at to get these values based on this chart here from the specifications. It's a little hard to see on here. I did the best I can. The blue represents 0 decibels from the original value. The outer green represents 1 decibel above the original value, and the inner green represents the 1 decibel below the inner value. So the goal of this exercise, as I sit on 1 kilohertz right now, and it's on the blue dashes, is to stay within the green dashes from 100 hertz all the way to 2.5 megahertz. And that would tell me that this oscilloscope is operating within the correct frequency response from the lowest amount of frequency response that I would plan to use all the way to the Nyquist, which is half of the total frequency that I would expect to use from this oscilloscope itself. So half of 5 megahertz, which is 2.5. Actually started this as low as 20 hertz. You can see 20 hertz does sit within the ±1 decibel. So we're going to make that our lowest point. So that one works. And obviously everything is being tuned in to read this chart, not to look at the waveform. And we can see 1K looks just fine as expected. That's our starting frequency. 1 meg also looks good. 2 meg shows a drop of just under 1 dB. 2.5 meg also shows a drop of just 1 dB, -1 dB. For the next set of measurements, the blue shows 0 dB, the outer green shows +1.5, and the inner green shows -5 dB. Again, 50 hertz within acceptable limits. If it was within 1 decibel, it will definitely be within 1.5. Without bringing it into sync, I brought it up to 1 megahertz, and we're going to bring it all the way to 5 megahertz and make sure that 5 megahertz stays within the inner green lines. That's going to be -5 decibels. So this is 1, 2, 3, 4, 5. So as per specification, 5 megahertz stays within -5 dB. Here's a last test that says when I go from 1 kilohertz to 3.58 megahertz, it should not drop more than 2.2 decibels. So my blue again is 0 decibels, and I've annotated -2.2 decibels in the green. So what I'm going to do is set up a test to change this frequency here from 1 kilohertz to that prescribed frequency and see what the output is. We can see that 3.58 megahertz sits right on the money where it should. Neg 2.2 decrease in frequency response as specified in the manual. 3.58 megahertz, and everything looks really good as far as the frequency response. I think I've exhausted all of the tests that are required. Here's another thing I've been noticing. If you look at the screen, as I zoom in to the best of my ability, it's really sharp trace, right? But as I come to this side of the screen, you'll notice that it's not as sharp off to the right. And I was concerned that perhaps there was a problem with the CRT. But as I look, and as I'm reading through the manual, it actually talks about that there was a compromise made in this design, and that there is a defocusing that's caused on the extreme right side of the trace, and it does not indicate a fault with the CRT, and it has to do with the amplifier design and sensitivity and bandwidth, and doesn't interfere with the normal operation of the oscilloscope. So apparently this issue is not a problem with the oscilloscope. Transient response has changed a lot with regard to frequency generators, function generators over the last 60 years. Obviously, it's also affected by the measurement is affected by the oscilloscope, but there is something to be said about even the field tech and its performance for rise and fall time. But regardless, even at 50 cycles per second, you're not going to see any rise and fall lines connected because they're so instantaneous at this speed that they're not visible. And in the document for 50, you're not going to see it. It's expected, if I could focus, it's expected that you're not going to see it at 1K or 100K either, but that you will see it at 1 megahertz. So we'll go through them right quick. This is 1K, and there is no visible line connecting the high and low peaks of the square wave. This is 100K, and there are faint faint transient lines that are connecting the peaks at this frequency. It's hard to tell from the manual. It's a copy of a copy of this is also exhibited in the book. This is 1 meg. It has a bit of a ring to it. I also get this on my other scope. I'm not using shielded cable. But as far as the waveform looks, it looks exactly as you would see it in the book in terms of the way the form is and the transient line connecting the peaks of it. So went out of focus there, but so pretty much what we expect to see in the book is what we're seeing for the performance of the square wave. Another test would be to take the output of this old holocrafters and push it into the input of this oscilloscope.
Both offensively and defensively, playing hard tonight. A lot of energy, really getting after the Cowboys and really winning.
Wood gave up a home run to Kipnis in last night's game. Rondon pitched 2 innings last night, but he's kind of moved to the back of the line after his late season injury. Carl Edwards in a...
I've connected up my tablet with some royalty-free music from YouTube, connected to my test Radio Shack amplifier and into the oscilloscope so we can see what some audio looks like pumped directly into this. Let's start now. One great test we can conduct is the phase relationship between two AC waveforms. And I happen to have set up on this Field Tech, one of the few functions it can actually do well is output 2 separate sinusoidal waveforms that can be configured independently of each other, as well as their phase relationship, which is kind of cool. I'm surprised that something as terrible as this function generator actually has this. I surprised myself with this. But I'm using it in XY mode, right? Or what we would call XY mode today, right? So vertical and horizontal input are configured separately, right? And the input is or the frequency selector is external, right? It's not the horizontal is not being done timed in any way. It's being timed actually by this input, right? And what I have is a 0 or 360 degree relationship, or what we would just call in phase. Two sinusoidal waves are completely in phase with each other, and we have a line that looks exactly like this. And if we weren't sure of ourselves, which we are, but if we weren't, we can look at this. The document here will also tell us on page 46 that we're correct, right? And I can bring this out of phase and sort of morph itself into a circle, and then come out of a circle and end up with a line in this direction, which would be 180 degrees out of phase, right? So in doing this test, it does, not only is it pretty cool, but it does illustrate the performance, the working performance of the oscilloscope very nicely. So we'll do that now, right? So we'll bring it up and slowly make our way. That's 30, 50, 60, 70, 80, and 90 brings us to a perfect circle, as you see here. And as we come out of 90, the relationship changes, and 130, 150, 60, 170, 180. And if we keep going, we will slowly make our way again. This is 210, 230, 40, 50, 60, 270. Again, a perfect circle. And as we keep going even further, we will find ourselves at 360 or 0, and start or end again where we started, back in phase again with both AC sinusoidal waveforms. As I'm set up in XY mode, I wanted to take this opportunity to look at some Lissajous patterns, and this field tech is able to do the different frequencies on channel 1 and channel 2. And what I've done is I've offset the frequency by a certain number of hertz in order to animate the Lissajous pattern even further. And it also outlines this on page 46 of the manual, right? So by doing so, I could have it come in and out of phase, animated. And what we're looking at is basically 1 kilohertz to 1 kilohertz ratio, right? But because it's going in and out of sync, we're getting this nice animated waveform. So here is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. We could get other patterns by doing thirds. This is 2.33310 to 1, right? And the reason for the 10 is only to be able to slow it down, because 2.333 would be too quick. If I were to just make it that, it would be a little quicker, but I could get it really slow. There's 2.33320. Now with that multiple, I can make more complex Lissajous forms like this. This is 4.333. So there are patterns that can be made at certain ratios, such as this. They get pretty interesting. If I go in the other direction, I get some pretty cool patterns too. I added 30 to them. 30 0.00030 to see what we get. That's 10 to 10. That is 10 to 9. 10 to 8. 10 to 7. 10 to 6. 10 to 5. 10 to 4, 10 to 3, 10 to 2, 10 to 1. I thought this one was particularly cool. I found this one. This is a ratio of 10 to 8.3333. Provides this pattern. So you just kind of stare at this for a while and go, wow. Then I found that this ratio, everything to .3333 is pretty cool. This is 10 to 7.3333 is also pretty cool too. You could stare at that for a while. We're going to mix up some of the waves in X and Y, but we can't make like both waves the same in some cases. Like this is what happens if you make both X and Y square wave. Pretty much no matter what I do, this is what's going to be on the screen, and it's not going to be very interesting. So what we're going to do is we're going to leave one of them sine wave and the other one square wave. So, and after this, we're going to do like one of them sine wave, you know, on one input and the other one sawtooth, right? But on the sawtooth, you could get away with a sawtooth and a sawtooth, but you can't really display a square and square because this is pretty much all you get. This is 10 to 1 square wave. You could just see one pulse at 1, right? I have a slight offset just so it oscillates, right? That's 1. There's 2. Now we see 2 pulses. There's 10 to 2. This is 10K to 3K. We see 3 pulses in there now. 4. 5 is interesting, right? So 5 again is one pulse doing a full sweep up and down. 6 has 6 distinct pulses. 7. 8. 9. And this is 10. This is 1 to 1 ratio. This is 10K to 10K. This is what a 1 to 1 ratio looks like with a square wave. Finally, this is a sawtooth wave, and we're going to work our way down from 10 to 1. This is 10, so it's a 1 to 1 ratio. This is 9, 8, 7, 6. There's 5, so this is 2 to 1. 4. Kind of looks like Pac-Man at the end. 3. 2. And this is 10 to 1. This is 1. This is a triangle on both inputs, not a triangle sine wave hybrid. So this looks a little bit different. Doesn't have the Pac-Man thing we saw before. It's a bit more boxy. The other two was a sine wave, and then we took obviously changed the horizontal input. But now we're going to go down and see what this one looks like. So we'll start at 10. This is 9. 8. 7. 6. This one's cool. This is 5, the halfway point. 4. 3. 2. 1.
I'll be using this oscilloscope for the restoration of amplifiers and guitars. It was a fun restoration project. Thank you all very much for watching. Goodbye.